system is stable. Hence the system is stable. This is how we can test the stability of a given system, stable or unstable. So we'll deal with some numericals based on the value of k, all those things in the next session. Thank you, Anil. So the examples which are given, posted on your group, you can go through it. The second problem, there are two sign changes. As there are two sign changes, so two roots are lying on right half of S plane, so the system is unstable. You can go through the second numerical which I posted on your group. So I will be dealing tomorrow with the other type. When G of S into H of S is given, open loop transfer function is given, how to proceed. So only thing is how to get the characteristic equation. Remaining procedure remains same one. So we'll discuss one such example in tomorrow's lecture. Then we'll move on to the calculate the limiting gain k. How much gain we can increase for a given system to be stable. Thank you. Thank you, Anand.
Good afternoon, dear students. So I will just highlight on what all we have covered in the yesterday's class. So we started with the performance of your transmission lines. So we happen to categorize the transmission lines into short lines, medium lines and long transmission lines. So up to 50 kilometers of range, they were grouped under your short lines. So 50 to 150 kilometers range, we have grouped them into medium lines, and above 150 kilometers they are considered as long lines. So even the voltage range was discussed. So we first saw the performance of short transmission lines. So since the length is small, there we have neglected the effect of capacitance. Then it was basically a RL circuit which we had to study and analyze. And then we started with medium transmission lines. So in medium transmission lines, as I told you, there are three methods for analyzing it. Either you have to adopt the end condenser method, or there is a nominal T method, or there is a nominal pi method. So all these three methods are based on the placing or considering how the capacitance value is to be taken into account. So in the end condenser method, what we did was we saw that your R and L are considered to be as lumped parameters, and the entire capacitance of the line is assumed to be lumped at the fag end of the line. So based on that, you all saw the various Phasor diagram associated with that. Then I think we stopped till there, and there is one problem now to be taken up with the end condenser method. Then I will switch over to your T method and pi method. So we will take up a problem on end condenser method now. So all of you, I request to kindly note down this problem. A single phase transmission line, 100 kilometers long. So when they give this range, so usually it is not specified, okay. So 100 kilometers, so you should be able to decide that it is a medium transmission line. So single phase transmission line 100 kilometer long has the following constants. So I will write the constants for you all here. They have given the resistance per kilometer as 0.25 ohms. Then susceptance. So I want you all to get aware with, see now, Z we usually express as R plus Jx. So I want you to know what is R, what is X. Then what about Y? Okay, Y is G minus JB, conductance and susceptance. So I want you all to be aware with all these terms. So susceptance per kilometer is 14 into 10 raised to minus 6 Siemens. Then reactance, per kilometer is 0.8 ohms, and receiving end line voltage is 66 kV or 66,000 volts. Assuming that the load capacitance of the line is localized at the receiving end alone, load capacitance of the line is, so I will just display the problem for you here. Simultaneously you can see it. Okay. Yeah, this is a problem. I have displayed it here. Assuming that the total capacitance of the line is localized at the receiving end alone. So that means what? See now, indirectly they are telling you that it is a end condenser method. Determine, first one, sending end current. Then second, sending end voltage. Third, regulation. And fourth, supply power factor. Okay, that is phi s angle they want to know. So indirectly cos phi s. The line is delivering 15,000 kilowatt at 0.8 power factor lag. Okay, so they have also asked to draw the phasor. Okay, so draw the phasor to illustrate your calculations. Okay, so first let us represent the circuit. So they have told all indirectly that it is an end condenser method. So I draw R, okay, lumped parameters. So this is R, this is X, okay. So to be precise, XL, then sending end current, okay. Then you have to show a load, okay, and then you have to show the end capacitor, okay. The current through it is IC, the receiving end current IR, receiving end voltage VR, sending end voltage Vs, and the capacitance value C. Okay, so accordingly the phasor, as I told you, first always consider the VR as your reference. Okay, so at an angle phi r is your current IR. Okay, so this is your receiving end power factor angle phi r. Okay, so you can see I start from here. Okay, VR, I represent IR. So now since it is an end condenser method, okay, the condenser takes a leading current. Okay, you represent it as IC, the resultant. So see, now this is IC, okay, and the supply voltage is, supply current is IS. Okay, so this is with respect to your current. So in parallel with IS, now I have to represent the drop here and drop here. So for the resistor part, okay, so there is no phase shift. So in parallel with IS, you draw and you represent it as IS into R. Okay, then here it is a purely inductive. So inductor, what we have represented, so it in 90 degrees phase shift represent IS into XL. Okay, and this resultant is nothing but, we can call it as IS into Z, and this whole I will put it inside so that I can draw the whole resultant. So this resultant is nothing but your sending end voltage Vs. Okay, so this angle between your Vs and Is is phi s. Okay, this is what is the phasor diagram for the problem. So we start with the analysis now. So what all they have given? So I will write first the total resistance. Okay, so the total resistance will be 0.25, it is 0.25 ohms per kilometer. So they have given the length of the line, so I will mention it here for your ease of calculation. So length is 100 kilometers. So everything with respect to 100 kilometers we will rewrite it. So it is into 100. So this comes out to be 25 ohms. So similarly, write down all the values for other things. So total reactance XL, okay, 80 ohms. Then susceptance, okay, so susceptance Y, it is 14 into 10 raised to minus 6 into 100. So this is 14 into 10 raised to minus 4 Siemens. Then receiving end voltage VR I will write. So VR is 66,000 or 66 kV. Okay, then next is I have to find out load current IR. Okay, so load current IR, okay, so that is equal to, what is the power they have given? Yes, it is delivering 15,000 kilowatts. So 15,000 kilowatts. So for kilo I am multiplying 10 raised to 3. then voltage is 66,000 volts, and power factor they have given as 0.8. Okay, so power factor, see 0.8 power factor lagging. So this answer comes out to be 284 amperes. Okay, then I'll write the value of phi r. So cos phi r is 0.8 and sin phi r is 0.6. Okay. So now referring to this phasor diagram, your VR will be the reference. So you can write VR is VR plus J0, okay, because that is the reference, so angle is 0. So your receiving end voltage is 66,000 volt. Then load current IR. So IR will be what? Cos phi r minus sin phi r. Okay, so cos phi r minus j sin phi r. Okay, so this comes out to be, so this IR we know it is 284. Substitute cos phi r as 0.8, sin phi r as 0.6. The value which they have, we have arrived at is 227 minus j 170. Okay, now here one more additional thing as compared to your short transmission lines is you need to calculate the capacitive current. Okay, so capacitive current, IC. Okay, so we have written the expression for that. So either you can take j omega c or you take jy into VR, admittance into voltage. Okay, VR. So this comes out to be 14, or you can keep the j term as it is, 10 raised to minus 4 into 66,000. So this is around J92. Okay, J92 amperes. So now we'll start with the first question. So they have asked first one, they want the sending end current. So sending end current is IS. So you can see from here, so IS is the resultant of IR plus IC. Okay. So sending end current. So phasor diagram is very important. So whether they have asked or not asked, okay, it is a good practice that you always draw the phasor diagram. So through phasor diagrams, many expressions without by hearting, okay, they are visible. Okay, so IS you can analyze easily from that. So sending end current, IS will be IR. Okay, so since it is phasor, I will just represent it like this. So this is 227 minus, where we wrote it, yes, minus J170 plus J92. Okay, so this comes out to be 227 minus J78. So magnitude of IS, okay, magnitude of IS is root of 227 square plus 78 square. Okay, so this is 240 amperes, first answer. Okay, then next I'll keep the phasor as it is. So let me write the calculations here below itself. Okay, so second one, they have asked voltage, they have asked sending end voltage, sending end current, sorry, sending end current, sending end voltage. Okay, so I will calculate the voltage drop. So the voltage drop is IS into Z. Okay, so across the entire circuitry, so IS into Z. So Z, as I told you, it will be R plus J XL. Okay, so when you substitute, you are getting the answer as 11,915 plus J 16,210. Okay, so sending end voltage VS Okay, it is VR plus, okay, the receiving drop plus the drop in that RL circuit. Okay, so VR plus IS into Z. Okay, so this comes out to be okay, so magnitude of Vs would have been, so I square it, 77,915 whole square plus 16,210 whole square. This the answer that comes out to be 79,583 volts, or you can also write it as 79.58 kV. Okay. So now next is they have asked percentage voltage regulation. Okay, so what is the formula for your voltage regulation? Sending end voltage minus receiving end voltage with respect to receiving end voltage. So we write here, so it is the third question, regulation, or you write percentage regulation. So what do we write? We write it as sending end voltage minus receiving end voltage divided by receiving end voltage into 100. Okay. So you have the sending end voltage now. Substitute receiving end voltage is 66,000. So the value comes out to be 20.58%. Okay. Then next is, see, it should be low. Clear? So if you are getting answer somewhere around 90 plus or something, there is definitely some error in your calculation, or the line is miserably designed. Clear? So it will be around this range only. It will be very less, up to 40-45% is maximum. So then fourth one, they have asked what? Supply power factor. So they want to know this value. Okay, phi s. Okay, the angle between Vs and Is. So I will write now. So see here, phase angle. You can write referring to phasor diagram. Okay, angle, phase angle between VR and IR, okay, is, okay, so you can call it as, say, theta 1. So it is tan inverse of minus 78 by 227. So it was, we had already got this expression, so the real and reactive terms, and so this comes out to be minus 18.96. Okay, so this is through that IS what I have got, and then phase angle between VR and Vs, okay, is theta 2 is equal to tan inverse. So which expression should I refer now? Okay, so here you can see, you got here now, okay, VR and Vs. Clear? So this expression you refer. So tan inverse will give you the angle between your VR and Vs. So theta 2 will be tan inverse 16,210 divided by 77,915. So this comes out to be 11.50 degrees. So therefore your supply power factor angle, okay, supply power factor angle phi s is equal to, so see now what will be phi s, it will be theta 1 plus theta 2. Clear? So we have calculated here, I think it should be, one second, yes, and IR. Yes, this angle plus this angle is total your phi s. So theta s will be 18.96 plus 11.50. So this comes out to be 30.46. Okay, so hope you understood, okay, what we have done here. Okay, it is this angle and this angle what we have calculated. Okay, so therefore supply power factor is equal to cos phi s, and it is cos of 30.46, that is equal to 0.86 lag. Okay, it is lagging. Okay, so you can clearly see here it is lagging because current is lagging behind the voltage. Okay, so that's it. That completes, I think, 4 questions have been asked. So this has come for, so in some papers it has come for 12 marks and in some paper it has come for 14 marks. Okay, on an average 2 to 3 marks per question what is being asked. Okay, so now what we are supposed to do? So now you studied the end condenser method. So now we will take up the nominal T method. So here you can see, okay, I'll just represent the circuit to you. So here what happens is, the parameters what you saw in the end condenser method, here they are divided by 2. Okay, the capacitance is assumed to be present at the center of the transmission line, and whatever R and L you all took up in the end condenser method, that has to be divided as R by 2 and X by 2 on either side of the line. Okay, so just see the representation. So this is the second method. Okay, so this is nominal T method. Okay, so very simple to understand. Okay. So here now I assume that it is divided by 2. Okay, we represent a load at the end. Okay, so you can call this as neutral. So here you have the sending end voltage. Okay. Then we have the sending end current. Then we are having here R by 2. We are having XL by 2. Okay. This is the capacitance. So see now it is been divided into 2 parts. Okay. So hence divide by 2. So here also it is same value. So don't use R1 and R2. Don't get confused with your transformer model. Okay. So here is your receiving end voltage. This is your receiving end current. Okay. This is the capacitance current. Okay, here is the sending end current, same is flowing here. So IC comes here, so you can give here as a drop V1, or you can also call it as VC, no problem. Okay, so this will represent the T model of the line. Yeah, so this is also known as nominal T method. So now I will draw the phasor. So just observe. So what happens? So first we will take your standard VR as the reference. So let me take it a bit short so that I can accommodate it here in the board. So this is VR and you can call it as A. So lagging to this will be your IR. Okay. So now VR and IR I have represented. So IC comes next. Okay, so I have IC will be leading. Okay, so IC will be leading IR. So it is 90 degrees phase shift. It is a pure capacitive circuit. So this represents IC, and the resultant is nothing but your IS. Okay, so this is IS. Clear? So now the angle between your VR and IR, okay, this is nothing but phi R. Clear? So phi S we'll see later. So now what happens? I have to represent the drop here, 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 and here. Clear? So here now I take this R by 2. So here also it is R by 2, XL by 2. So first we start with this part. So in parallel with the IR what I have drawn, I have to represent IR by 2. Okay, so here now at this tip, so see the voltage. Okay, so this one in parallel with IR, so I represent IR into R by 2. Then, okay, it is a inductive circuit. So again you show here pure inductive. IR into XL by 2, and what is this? Okay, this is, see, this represents the drop here. Okay, so I am drawing the drop here. Okay, so this is nothing but IR into Z by 2. Okay, now I have to represent the next drop. Okay, so here in parallel with IS, and this is also perpendicular to that, IS into R by 2. Okay, so now here see, okay, in parallel with IS, I draw what? IS into R by 2. Okay, then again there is a 90 degrees phase shift because of pure inductive circuit. So it is IS into XL by 2. And what about this? So this will be IS into Z by 2. Okay, so I represented this drop now. Okay. And the final resultant, so this resultant was what? So this is nothing but V1. Clear? So here if I join, okay, so this will be your V1, and your final resultant, this is your Vs. Okay, and the angle between your Vs and Is is nothing but phi s. Clear? Okay, so I give the names here. So let me stick on to what I have written in your notes so that it will be easy to follow. So this is C, D and E. Okay, hope the phasor diagram is clear to you. So start with VR. Okay, lagging behind is, so this is a load, we don't know the pattern, so just show the lagging angle. So there is IR, okay, and then there is a leading current which is being taken by this capacitance. Show the leading current, and what will be the resultant of that IR and IC? That is nothing but your supply and supply current IS. Okay, so now in parallel with your IR, okay, I have to represent IR into R by 2, and with a 90 degree phase shift IR into, and this is IR into Z by 2. Okay, and this entire resultant is nothing but the voltage drop which is occurring here, that is V1, the drop across your capacitance which is considered. Okay, then next I have to represent this drop. Okay, here there is a current IS, so in parallel with your current IS, you draw IS into R by 2. Okay, 90 degrees phase shift IS into XL by 2. The resultant is the entire drop here, IS into Z by 2, and this whole resultant will be nothing but your supply voltage Vs. So this Vs will comprise of so many drops. Okay, hope it is clear to you. Okay, so now we write the expression. So the entire line capacitance is assumed to be concentrated at the middle point of the line, and half of the line resistance and reactance are lumped on either end of the line. Okay, so full charging current flows over half the line, and here we have considered one phase. Okay, so load current IR, so I am writing all the expressions. So load current IR will be IR into cos phi r minus J sin phi r. Okay. So V1, this is same what we have written for previous medium transmission lines also. Okay. End condenser method, VR plus IR into cos phi r minus J sin phi r. So I repeat again, you are not having any derivations, okay, but just you need to know these basics, so I am mentioning about this. Okay, so this V1 I am writing. Okay, so V1 is VR plus this, okay, so plus this I am writing, IR into Z by 2. Okay, then here you will get the capacitive current also. So IC is J omega C into V1, okay, or you instead of omega you can use 2 pi F C into V1, okay, very important term. So you remember this, okay, this is often asked, what is the capacitor current, okay. Then sending end current, I'll write here. So sending end current IS okay, so IS is equal to IR plus IC. So you have the expression for IR, you have the expression for IC. IS is IR plus IC, and then sending end voltage Vs will be what? V1, okay. So Vs is equal to V1 plus Is into R by 2, okay. So V1 plus this drop, okay. So Vs is V1 plus this drop, Is into R by 2 plus J XL by 2, not Z, okay, this is 2, J XL by 2. Okay, so these expressions you ought to know for solving the problems. Okay. So what is the time? Yes, we can take up one short problem on T method, and the Pi method will be explained tomorrow. So take down one simple problem here. Here, note down. A three phase 50 hertz transmission line, a three phase 50 hertz transmission line, 100 kilometers long, 100 kilometers long, delivers 20 megawatts, delivers 20 megawatts So I think I have the problem, just a minute, let me check. Yes, this is three-phase 50 hertz transmission line, 100 kilometer long, delivers 20 megawatt at 0.9 power factor lagging and at 110 kV. The resistance and reactance of the line per phase per kilometer are, yes, here is the, here is the problem. delivers 20 megawatt at 0.9 per factor lagging and 110 kV. The resistance and reactance of the line per phase per kilometer are 0.2 ohms and 0.4 ohms respectively, while the capacitance admittance is 2.5 into 10 raised to minus 6 Simon per kilometer per phase. Okay, so you have to observe here all the values that they give will be per kilometer basis. Calculate the current and voltage at the sending end, efficiency of the transmission or efficiency of the line, and they have specified use nominal T method. Okay, so use nominal T method. So the same phasor diagram what I have drawn here, okay, you can see. So they have distributed the parameters R by 2, XL by 2, R by 2, XL by 2. Okay, on this end you have the sending end current, then we have the capacitance current, the capacitor see here, receiving end current, receiving end voltage, and this they have represented as the drop V1 or Vc, okay, anything, and this is the voltage, supply voltage Vs. So based on that, the phasor diagram is being given here exactly similar to what I have drawn here. So we will just start the calculation. So here now you have to be careful while calculating the voltage. Okay, so since it is a three-phase system now and we had considered the per phase analysis, so you have to write the voltage properly. So they have given the receiving end voltage as, okay, so it will be a three-phase voltage, so you have to convert it to per phase. Your all analysis is per phase basis. So per phase means you have to consider root 3 factors. So 110 into 10 raised to 3 divided by root 3. So this gives me the voltage per phase. So this is around 63,508 volts. Okay, then you calculate IR. So they have told it is 20 megawatts. Okay, am I right? Yes, it is 20 megawatts. So load current IR is 20 into 10 raised to 6. Okay, divided by power root 3 VI cos phi, that you have to remember. Okay, into 110 into 10 raised to 3 into 0.9. Okay, so this comes out to be 116. Okay, so here voltage you don't change. Here you have to take three phase voltage only. Fine. Okay, so this root 3 is nothing but your power expression. From there it is coming root 3 VI cos phi. Okay, so this is 116.6. So they have given cos phi r as 0.9 and sin phi r as 0.435. So it will be, you take the angle and find out sin phi r. So we will start with the first one. They want what? They want the current and voltage at the sending end. Okay. So VR is what? VR plus J0. So this is 63,508 volts. Then load current. So please you refer for every expression what I write, please refer the phasor diagram. So load current IR will be IR into cos phi r minus J sin phi r. So you have both the values, so it comes out to be 105 minus J 50.7. Then capacitor voltage or voltage across C. Okay, so it is V1. So you refer to the phasor diagram. So what will be V1? V1 is VR plus IR into Z by 2. Okay, so you can see here also. V1 is VR plus IR into Z by 2. Okay, so this value turns out to be 65,572 plus J15 93. Okay, then charging current you calculate. So charging current or capacitance current. So IC will be, okay, J into, okay, Y into V, okay, V1 to be precise. So this comes out to be minus 0.4 plus J 16.4. Clear? So your Y value is 2.5. They have given there. Okay, so total capacitance or admittance per phase is given there. So it is 2.5 into 10 raised to minus 4. Okay, so here we have written here total values. Okay, so this is 10 raised to minus 4. Okay, so from this now I will calculate sending end current. So what is sending end current? So sending end current IS will be, so please refer the phasor diagram, it will be IR plus IC, and this comes out to be 110 at an angle minus 18.9. Please verify this at home and please get back to me if there are any discrepancies. Okay, so we shall soon have a Google Meet to discuss your problems. So you can say magnitude IS is 110 amperes. Then sending end voltage, okay, so Vs will be V1 plus Is into Z by 2. Okay, so these things are very simple to write if you are able to draw the phasor diagram clearly. Okay, very easily. So see here you can see Vs is V1 plus this drop. Okay, so this comes out to be 67,304 plus J 3342. Okay, so your magnitude of Vs will be, you square it, square root of this square plus this square. So it comes out to be 67,387 volts. And then what will be the line value? Okay, this is phase value because you have considered per phase there. So line value multiply by root 3, that's it, line value of sending end. So this is one care that you have to take here of sending end voltage. So same way even in pi method. Okay, so we'll see that tomorrow. Okay, but as of now finish off this problem. 67,387 into root 3. So this comes out to be 116. Okay, 0.717. So one biggest cross verification. Clear? So line initially you all calculated no per phase voltage. How much was that? You all wrote one second. Sending end voltage, receiving end voltage. Yes, receiving end voltage should be less than the sending end voltage. So receiving end voltage, how much you will have got? 63.508 kV. Yes, so compare the values. So Vs should be more than Vr. So that is one cross verification. And finally, the third one they have asked is they've asked transmission efficiency. Yes. So now you know the power. So how much they have given? Power 20 megawatt. Okay. So how do we define the transmission efficiency? Output by input. So they have given the output as 20. Now what will be the input? Input will be output plus losses. Clear? So now we don't know the losses. So transmission efficiency is 20 divided by 20 plus that losses. So losses are nothing but your I square R loss. So now we will just calculate the losses and then put it in your efficiency formula. So total line losses for the three phases Okay, so this will be 3 times Is square into R by 2 plus 3 times IR square into R by 2. Okay, so this circuitry here, clear? So drop here plus drop here. Okay, so here it is IR, here it is Is. 3 lines, so 3 times the drop. So this comes out to be, so you know all the values, so substitute here and you just take the magnitudes. So this comes out to be 0.770 into 10 raised to 6 watts. So 10 raised to 6 is nothing but mega. So you can write it as 0.770 megawatt. This is your losses. So what will be the transmission efficiency? So the transmission efficiency is, I have told you, okay, output by input. So output is 20 megawatt plus your losses is 0.770. Okay, so work out the answer. You can say into 100 if you want. Okay, you can say transmission percentage transmission efficiency. So we'll write into 100. So this comes out to be 96.29. Okay, so highly efficient. Okay, so this is again the range of this question occurrence, sometimes 10 marks and in some papers it has come for 12 marks. Okay, so on the similar lines, tomorrow's class we will discuss the nominal pi method. So in pi method what happens is, the parameters are lumped at the center and this value of capacitance is assumed to be distributed half each on both the ends. So that concept is very important even with respect to your further semester point of view in power system analysis, you say, or in computer techniques in power system analysis. You need to know the models very clearly, nominal, the T model, the pi model. So later on we are going to generalize these values, okay, they are known as generalized constants or ABCD constants. So with respect to the pi model, you will be evaluating the bus admittance matrix Y bus in the further semesters to come. So you please pay attention to the tomorrow's method, and then we'll take up some problems on pi method. Then we'll briefly discuss on what is long lines, okay, we don't have any derivations for the long lines. And then directly I will start with what is meant by this ABCD constant and what are its values for short line, medium line and long lines. Okay. Yes, I will just show you the problems that I have included in your notes. So you can just observe there on the screen. Okay, so many problems, solved problems are being included. I will also float some assignments wherein you are having unsolved problems. Okay, so here one sample I have included and later in the earlier part there are many problems included. So today's suggestion for you is please go through the notes, okay, what I have given to you, the e-notes what I have given to you, completely scan, okay, solved problems, unsolved problems plus my handwritten notes are there. So please go through that and you can ping me back on WhatsApp. So if you have any discrepancies, please ping back or please call back. Okay, all your doubts will be addressed.